Eric, please.
Okay. Thank you very much. It's a pleasure to be giving this talk. I'm going to have to spend a minute sharing with my iPad so that I can take notes. So please bear with me. This might take a sec.
Yeah, and by the way, slides of your talk are now sent to everyone in the chat. There will be a lot of pictures, so
Right.
you should better download them.
I don't, yeah, okay. I gave the same talk recently and I shared it, but this is only my second Zoom talk. So
Okay.
can you see the shared screen at this point?
Yes.
Okay. So now I just have to open the right app. And
Great.
okay, I think we're ready. Thanks. So maybe in the context of this seminar, I should warm up a bit by saying why I'm interested in Legendrian surfaces. As you may have seen, it's a talk about Legendrian surfaces and some categories you can construct from them and some moduli spaces of objects.
One technical thing, is it your intention not to show all the page, the whole page? Because,
like this?
Yeah, okay.
That's pretty much the whole page. The way I have the pages are basically half filled. So when I need to add on to it,
okay.
I can. But also I think it's maybe, I could show more. How's that?
No, that's fine.
Okay. Sure. Right, so why study Legendrian surfaces? So really the reason why I got into the study of Legendrian surfaces is because like many people, I'm interested in Calabi-Yau threefolds, often non-compact Calabi-Yau threefolds, and the brains that can lie in them, and the models that you can make for quantum field theories using brains. And so in the context of a non-compact Calabi-Yau threefold, when you have a Lagrangian three brane, you might put a boundary condition at the end of the non-compact Lagrangian three brane, and that would be a Legendrian surface. So that's really the motivation behind a lot of this. And the moduli space of objects in the category of Lagrangian three branes bounding this Legendrian surface is really the moduli are the moduli spaces which will arise in this talk. Okay, so that said, let me now put that aside unless there are any questions about the motivation. Okay. All right, so this is a talk, as I said, about Legendrian surfaces. So let's begin. Let's go back to knots because the study of knots will really guide our study of surfaces. So every knot is a braid closure. Alexander proved this in 1923, but not uniquely. So many different, there are relations in the braid groups, and even braids of different number of strands due to the Markov relation can define the same knot. But because every knot is a braid closure, we might begin by looking at a neighborhood of the circle. And so the contact counterpart, because we're interested in Legendrian knots and Legendrian surfaces of neighborhood of a circle, would be by Weinstein's neighborhood theorem in contact geometry, the first jet bundle of the circle, which is S1 cross R2. So let's see, can you see, I need to have a cursor. If I do that, is that visible?
No.
I don't see, right, it's not.
Oh yeah, now it's better.
Oh, okay, you can see this purple? I can't see it.
No, I see. The arrow moving.
Oh,
It's not.
that's,
Yeah, but
no, that's strange because, so you can see this, this arrow moving around, but
yep.
you can't see when I'm marking up my screen, my iPad.
No, actually, from my limited experience, iPad doesn't have some features
Ah.
yeah.
I see.
Of the
It did
normal.
work last time I gave this talk, so I don't know if anyone in the audience has expertise in the matter. Please let me know. If not, then I'll just have to use this cursor, and I won't be able to mark up the pages. So I apologize for that. What about this? When the screen goes up, does it go up for you?
No.
No. So it's frozen.
Yeah, this is what happened.
It moved last time when you scrolled it up and down, but it's not moving right now. So something happened between then and now.
I see. Yeah, and I wouldn't know how to fix that except to unshare and then reshare.
Okay.
I'll try that. Ah, I see now the purple is here. You can see this purple now?
Yes, can you move the page?
Yes, the purple has appeared.
Yeah, but it doesn't appear live when I move it.
And also, can you change pages?
No, I can't.
Yeah, that's more important.
Don't know what to do.
Yeah, there are a few options. At the very last resort, since everyone has your slides, you can move pages on your side and tell people where to look at, but it's kind of,
Oh, I see. Yeah, it's very slow. Now some new purple is appearing.
Yeah, you know, New Zealand is very far, so maybe it's...
Yeah, so... okay, right.
Or maybe you can directly connect your iPad to Zoom.
Yes, I'll try that. And then I'll mute that. Okay, so that's, let's do that right away. Apologies. All right, so we're looking at first knots in near as braid closures, and their Lagrangian counterparts would be near Weinstein neighborhood of a circle, which would be the first jet of the circle, which is S1 cross R2. So we're talking about a solid torus and not knots in there. And so what I've drawn here is a projection. So of course we study knots from their projections, and in contact geometry you have two interesting projections. So the first jet of a space, you think of a function and its values. You can see the cursor circling the R?
Yes.
Yes, yes. Okay, so that's the values of a function, and the differential of the function would be a covector. So the first jet is the cotangent of a space cross R. And therefore, there are two natural projections, one to the cotangent itself, that's called the Lagrangian projection, and one to S1 cross R, the space cross R. So, for example, since we're interested in a circle, if I have an angular coordinate theta, and I have a function of theta, I can look at the graph of the first jet of that function, which would be the set of points theta, comma, f prime of theta, comma, f of theta. And if I project to the first two, that's the Lagrangian. And you can see this projection is just theta, comma, df of theta, which is the graph of the differential of a function, which will be an exact Lagrangian. And then the other projection is to S1 cross R, which is the theta and the value of the function. And that's called the front projection. And no matter the dimension of the manifold, it's always, this front projection lives in one higher dimension. So when I take this image of this graph, it's just a hypersurface. Now, a submanifold is Legendrian if the canonical one form defined by dz, z being the coordinate here on R, minus y dx, which is the canonical one form on the cotangent, if that vanishes, or the distribution defined by the kernel of that one form is the contact distribution. So you can see that if I set alpha to 0, that I can solve for y is dz dx. Or if there are more coordinates, y is the partial of z, yi is the partial of z with respect to the xi. So in other words, you can recover the third coordinate. So the front projection is very useful. So here's a picture. This is the angular coordinate, and I have some multi-strand braid. And I'm looking at, so I have a multifunction, f1, f2, f3, and so on. And I just look at the graphs of those different functions. And you can see that the braid will cross itself in the front projection, although because the slopes of these two lines at the cross are different, that extra coordinate will be different, and there's no intersection. So this is a smooth one manifold here. Okay. And so crossings of projections of knots is nothing new, and there's not much new in really our approach. But I could project further down to S1 and just record where the knot crosses. You see, here 1 would be the crossing of strands 1 and 2. 2 means the crossing of strands 2 and 3, 1, and so on. And the Markov move, which you can see doesn't lie in S1, but if we were in R3, the Markov move adds another strand and a crossing, and you could just sort of loop this green loop over the top and undo that crossing. And so that would define the same knot. Does that make sense? If this was not a cylinder, but rather a cap, then this extra loop from this green strand can be undone, untwisted around. Okay, so the more efficient encoding of the knot would be just by recording these different crossings, which would be a labeled, a colored set of points, colored by the different crossings that occur. Does that make sense? I need to look for some confirmation. I see a lot of
yeah, okay, yeah. I mean, it doesn't make sense.
Hi, Pang. And sorry, yeah, so I hope people have bared with me. Gabe gives me a thumbs up. Thank you, Gabe. And Denise out there.
Sorry, quick question.
Yes.
The one you've drawn, is that the front projection or the Lagrangian one?
This is the front projection.
Okay, thanks.
Yeah.
S1, it's not kind of, they're very close.
Well, yes, they look too similar, but yes, okay, thanks.
Yeah, in one dimensions, it's maybe too close. It'll become more clear. Okay, so we're in. So now we just do the same thing for Legendrian surfaces, exactly the same rationale. We look near a two-sphere, a Legendrian two-sphere. Now we'll have some multi-sheeted cover over the two-sphere. And I've tried to draw on that in these pictures. Downstairs here is the two-sphere, or a piece of the two-sphere. And above it, you see, in this case, a three-sheeted cover. And the sheets are crossing here. Here, the first two sheets are crossing, and here, the second two sheets. Sorry, the second and third sheets are crossing. And so if I have that, I just record that information by a colored line, colored edge. So that's maybe an easier thing. Now here, you can have, in 2 dimensions, 3 planes meeting at a point. And in fact, that will happen. And so what that means is that these lines where there are crossings will themselves meet. in this kind of pattern. So due to my tech problems, I'm not able to annotate the screen, but if you were going to draw some coordinate axes for your calculus class, you would draw it like this here, typically X, Y, and Z, right? And so what you're really drawing is 3 planes, the 3 coordinate planes, and you draw them as dotted lines when there's a plane, obscuring the crossing along that axis. And that's exactly the same picture that we would have here. So if you just look into the corner of the room and imagine that it was translucent, you would see exactly this.
Can I ask a question?
Yes, please.
Is it also the case that these things are not actually intersecting in the jet?
Exactly, that's right. If you just look at the corner of your room, you see that the normal vectors of those planes are all different, and that means that the extra coordinates, which are the partial derivatives of the heights of the planes, will be different for the 3 sheets.
From the Lagrangian perspective, should I think of this N-to-1 color as sort of a spectral surface?
Yeah, we'll yes. That's right. This is some sort of Lagrangian spectral surface that we're discussing.
Sorry, just one question before you go on. So the 3 lines, you have 3 planes, so shouldn't you have 3 colors instead of 2 colors? Because you have.
That's a great question. The colors are labeling the crossings. So if we have 3 sheets, you can have crossings of 1 and 2 or 2 and 3, and that's it.
Yeah, and I mean in the middle picture.
Yes.
Down here, shouldn't you have like a 1, 2, 2, 3, and 1, 3?
Right. One can never cross 3 without going through 2, right? They're ordered by their height.
I see. It's not labeled by who cross with who.
It is labeled by who cross with who, but the only crossings possible are 1 meets 2 or 2 meets 3. 1 and 3 can't be at the same height. Let me go back. Remember, the 3rd coordinate is the height of the line. So this line can't meet that line without going through this line in between somehow. It's only adjacent.
Okay,
surfaces.
you're not giving each strand their intrinsic labeling. You're labeling them. They will switch label whenever they cross each other.
That's right. They're labeled by their height. That 3rd coordinate is the height of the strand.
Okay, good.
Thanks. Yeah, that's a very good clarification. So sort of more generally, what is this? These crossings are the Weil group, and the Weil group of GLN is what S.
So these are just permutations.
These are the elementary permutations. That's right. Okay, so this is all sort of not much happening. The one interesting thing that happens is this potato chip here, this 2-sheeted potato chip. So you have here, I have just 2 sheets, not 3, and they're crossing each other along this pattern. And you see that the crossings themselves meet. And where they do, you have this Y vertex or trivalent vertex. Now, this is something that's non-generic. There's a local, we can write a local model for it. If you just write the complex cusp, t squared, t cubed in complex coordinates, you can write a local model for these 2 sheets. And what happens here is at the center, you actually have a tangency of those 2 planes. So there is what you have then is a 2-to-1, a branch covering with a branch point here. So in the actual surface upstairs, the Lagrangian surface, which lives in 5 dimensions, the first jet of S2 is a 5-dimensional space. The Lagrangian surface is smooth, but the projection is singular at this point, and you have a branched 2-to-1 cover. So this is just like the covering, Z goes to Z squared. Locally, it just looks like that. In fact, if we had looked at the Lagrangian projection instead of the front projection, it literally would have been that. So that's new information. This is a kind of non-generic front for a Lagrangian surface. And Arnold classified kinds of fronts that can appear and gave this one D4 minus wavefront singularity. It's non-generic, just like if you have three lines in two-dimensional space, in a one-parameter family, they will meet at a point. But generically, only two of them will meet at a time.
So would the generic perturbation of this bring forth a triangle of cusps or something?
Exactly, exactly that, yes. I wish I could draw it here. This would go out a little bit here, and then there would be a cusp, 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 right? And there would be three swallowtails.
Swallowtails, yeah.
Exactly that. Okay. So now you can already see what to do in general. We'll define an n-graph to be a collection of embedded cubic graphs, since this trivalent vertex is the only thing non-trivial that we're going to consider, on surface S, such that when they intersect, they can the ith one can only intersect the I plus 1 at vertices, just as you have here, whereupon the edges interlace, just like this pattern here. So what you have is sheets, three sheets intersecting at a point in three-dimensional space, and when that happens, you have this interlacing pattern, just like we discussed about the way you draw your coordinate planes in calculus. And now from this, we can construct a Legendrian surface up to Hamiltonian isotopy. And we define the weave based on this n-graph to be the surface so described up to 3D isotopy. Okay. And having done that, we're now going to define the category that I was mentioning. So given such an n-graph, namely a collection of colored graphs that intersect with this interlacing pattern, for the neighboring ones, we construct this Legendrian surface, and given a Legendrian surface, we can define a category, and it's going to be the category of constructible sheaves on the surface cross R, which is the space in which this front projection lives. And they're going to be, there's some decorations, they're going to be simple sheaves, and we can, I probably won't get too far into that. But the sheaves will be micro-supported along this Legendrian surface. So my intent wasn't to go too deep into this category, but I can explain roughly. If you have a hypersurface, it induces a stratification of the space. And these sheaves are locally constant on that stratification. So what that means is that in between the sheets, what we're going to assign is a constant vector space or chain complex, if we consider chain complexes of sheets. And then those vector spaces can change across the sheets themselves, but in a prescribed way. So this one says that the rank of them will differ by 1 on opposite sides of the sheet. And there's some more detailed conditions, but we can get into that later on.
So this is a derived definition, yes? So it's complexes.
That's right. These will be complexes of sheaves, but in the case under consideration, the moduli spaces of such objects are going to be ordinary spaces, smooth spaces. If there's any stackiness, it's just a teeny bit of it. And that's what this one does. The fact that they were only that they differ by rank 1 really allows for a linear algebraic description of the set of objects.
And the sheaf here is coherent or constructible or?
Constructible sheaf. So it's just a topological thing. On an open set, you give a chain complex. And so we're going to define the moduli space of objects, this M of, what do we call this? Some script M of lambda. Okay, let me give you more details on how to define those spaces. So let's go back one dimension. In 1D, we had these different strands crossing. And let's discuss what this moduli space looks like. First of all, way down at the bottom, below the front projection, we're going to have 0. That's going to be, we're going to always do that. Then, as I said, as you cross the front projection, you pick up one rank of your vector space. So if it was dimension 0, it's now going to be rank 1. So V1 is going to be a rank 1 vector space. V1 prime may be a different rank 1 vector space, and so on, V2 and up. So you see, as you go up on the left side, you get a flag. And then in between these dots, you get a flag, 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 bunch of flags. So this moduli space is going to be, you know, some subset of product of flag varieties. And in 2 dimensions, it'll be the same thing. 0 at the bottom, you cross the surface, you pick up one rank, you cross it again, you pick up another rank, rank 2.
So Eric, in 1D, this is a picture for the Stokes phenomenon for irregular connections on, say, whatever your surface is, and in dimension 2, does it have a similar?
That's a great question. I very much wanted to find such an answer, but I don't think that there is such an answer. So in 1D, what Jan's saying is that these same patterns arise when you look at the Stokes braiding of an irregular singularity of a differential equation. So you could then look at a D module in complex 2 dimensions, and then the pattern would be something regarding a 3-sphere rather than a 2-sphere. But I think simply that there's just a lot more freedom in this language of topology and constructible sheaves than there is in the algebra of singularities of holomorphic functions.
Okay. And in terms of flag at the intersection points, so the flag length will just reduce by 1.
Sorry, can you say it again? I missed it.
The length of the flag at the intersection point.
Yes. Yeah. So I haven't discussed how the neighboring flags are related to one another. I'll do that next.
Okay. Thank you.
Great question. Yeah. So there is a condition, and this comes from this singular support of these constructible sheaves condition. And the condition at a crossing is that these 2 vector spaces are transverse. So this was rank 0, rank 1, rank 2. These 2 rank 1 vector spaces are subspaces of this rank 2, and they must intersect transversely. So that their intersection is this 0-dimensional space, and that they span that. That's not, I'm not imposing that. That comes directly from an analysis of what this means. What are the objects that have the desired singular support? Okay, so that's what we call the crossing condition. Where they cross, there is that condition. Okay, so what that means is that this flag here, in between the blue and the red dot, is not that much different from this flag. Look, this space is the same, that space is the same. The 2-dimensional space is different a little bit, and then the 3-dimensional space is the same. And how different is it? Well, it has to be transverse to the old one. And so in fact, a priori, you would have a P1 versus worth of other possible flags, but we remove one of the points in that P1, and so you have an affine lines worth of other possible flags. Without that extra condition, what you would have here is a flag, and then a P1, an extra P1, and then another extra P1, and another extra P1. And so what you get is the Bott-Samuelson variety is a P1 bundle over a flag variety, and then a P1 bundle over that, and then a P1 bundle over that. So that's called an iterated Bott-Samuelson variety. And we have some open version of that. And the same is happening over here, only there's not like a linear direction of the iteration. So you'd have a flag here, and then over here, a neighboring flag where these 2 lines in that flag are distinct, and this one is distinct from that, and so on. That makes some sense? Pang?
Yeah, it does. I don't know.
Yes.
Should I reply for everyone? Pen,
No,
Pen,
yeah, I was asking Pang. I was
Pen.
asking
Okay,
Pang.
good.
I saw his face.
Yeah, it's
okay.
like girlfriend seminar. One should understand everything. One person.
All right. Well,
So maybe why would
so
you?
it
for
will
better or
be
for
fun.
worse, I didn't grow up in Russia, so I don't I don't understand everything.
Okay, let me try to understand. So can I regard that as a, I mean, in the curve case, that's a map into the flag variety, but at a certain point that flag degenerates. And in the surface case, that this time is not a curve, but it's from a surface map into a certain flag varieties, but along
I wouldn't say that the
certain
flag
point.
degenerates. I mean, these flags do not vary along until you hit the crossing. So it's just a flag, and
That's
then
right.
another
That's
flag.
right.
The
That's right.
discrete set of kits.
Mm-hmm.
Okay. Now, as I said, the surface or the knot is not unique. There are relations. So the Reidemeister relation says that 1, 2, 1 is equivalent to 2, 1, 2. And if you do the isotopy that affects that relation, you can see it looks like this. Here's 1, 2, 1, and then as you take a movie of the isotopy of that Reidemeister move, what you get is a surface, and what we discover is one of our sort of basic building blocks of their surfaces really encodes the movie of the Reidemeister 3 isotopy. If I take a movie of doing Reidemeister 3 and then undoing it, so you have this movie here, that isotopy is actually equivalent to not doing anything at all. And this is a local relation in the patterns that we draw, which we call the candy twist. So what this says is that if you have a flag here, and then this is meant as a local relation. So if you fix the boundary conditions by putting flags here, relatively transverse to each other as described up here, namely here they're two-dimensional spaces would differ, here their one-dimensional spaces would differ, and so on. That's equivalent to doing nothing at all. And one thing you can say is that these flags in between are fixed by the boundary data. If they were not, then this diagram could not possibly be the same as that one. Let's see if I can explain how to do that. If I have two flags that are different, so transverse, so that would be like having a point and a line. The way, and then here's on the right side is another point and another line. And I apologize that I can't annotate very well. But what you can do is first move point A to the intersection of the two lines, and then change the line to be the same as the other line, and then change the point to be the same as the second point. And that would take you in a path of flags from this one to that one. But you could do that in a different order. You could first change the line to be, to go, so you have 2 points from the two flags, and each point has its own line. You look at my hands. And then you can change the line first to go through both points, then change the point, and then change that line to be the second line. So that represents the choice up top versus the choice through the middle. I don't know if that got through. That was maybe a little bit challenging to follow. Another isotopy that will lead to a relation among our diagrams is moving a plane. So here we have this potato chip, and in green I've drawn a third plane, and you can see that that third plane will intersect the two slices of the potato chip in different ways. So I've colored one blue and one red, and then this line going through is where the potato chip just intersects itself. So this would be the diagram of a potato chip plus the third plane. Now what you can do is move that third plane through across where the potato chip intersects itself. Now you see that the slope of the potato chip and the slope of the third plane, which I'm indicating with my hands, are different. So as you move it through, you're not creating any intersections among Legendrian surfaces. And we call that the push through. And after it goes through, it's maybe a little bit more challenging to see. The intersection pattern becomes a little bit more complex, but it becomes this. So these two graphs represent the same Legendrian surface, just as these two diagrams represent the same curve, just related by a Reidemeister isotopy. Here, these two Legendrian surfaces are related by this push-through isotopy. There's one more relation, which may be of interest, may not. If you have 4 planes, let's say 3 of them are the corner of the room, and the 4th one is a diagonal one, you can then take that 4th one and push it through the corner of the room. And you would get a whole new different pattern. And this is called the Zamologikov relation. He found this by studying consistent scatterings of one-dimensional objects in integrable theories.
And can you sort of look for solutions to Zamologikov tetrahedral equation, like working with certain sheaves, constructible sheaves with micro-local condition on these Legendrians?
I don't want to answer off the cuff because I hadn't thought about it.
I have a much more basic question, if you'll allow me.
Yes, please.
Could you, I mean, if you were not planning to, maybe you can skip it, but could you explain the numbers next to the?
Sure, yeah, absolutely. But where did the question come from? I can't see all the speakers, so I'd like to.
Oh, I'm Tushar.
Oh,
My
okay.
video is not working, sorry.
Oh, okay, okay, great. Sure, I'm happy to explain that. Yeah. So if
and could you
remember each.
Sorry, could you zoom in a little on that picture?
Sure.
Yeah.
How about that? Okay. So what you think of, so as we saw with this Reidemeister move, when you have one of these relations, you can think of it as a movie of relations of something one dimension down. So if I took a movie here by taking successive hyperplanes or lines, what would happen when I did that? So let's see, let me see, 2, 1, 2. Right, what happens along the outside of this? I see a 2, oh, I'm doing it up here. See this purple arc here? What do you have across the top along that arc? You have a red, blue, red, green, red, blue, red, which I'm encoding as 2, 1, 2, 3 is green, 2, 3, 2, 1. Does that make sense?
Yep.
I think this purple arc goes from 2 red, 1 blue, 2 red, 3 green, this extends, and then 2 red, and then 1 blue.
1 blue, yeah.
Yeah.
Mm-hmm.
And then maybe closer to the center, you would have this crossing. And so as you go through this crossing, this is a Reidemeister move, which replaces the 2, 1, 2 by 1, 2, 1. So you see 1, 2, 1, 3, 2, 1.
Yep.
And then as you go further and further, you get this successive sequence. So these knots are all equivalent. These are just different expressions of the longest word in the Weil group of, in the braid group of 4 strands.
Right.
And these are different equivalent expressions of that. Yeah.
Perfect. Yeah, thank you. Thank you.
Sure.
That was very helpful.
Okay, and then there's another relation which is analogous to the Markov move, which doesn't pertain to looking at J1S2, but maybe in looking at the flat 5-dimensional space, R5 or S5, where you can add an extra sheet to the surface and then close it up in some way. I don't think I'm going to focus on that. But these two diagrams, this one G with all these decorations, would give the same isotopic Lagrangian surface as just this plane G if you looked in R5 or S5, but not if you looked in S2 cross R3, which is the first jet of S2. Okay. Okay, so now let's look at the moduli spaces here. If I only have a two graph, two sheets, there's not much to do. You only have this cubic graph. So here, you see this is the edge graph of a tetrahedron drawn in a round way. And here's another one. Ignore the blue, just look at the black graph. That's a cubic planar graph. And the Lagrangian surface here, as I described, would have would be branched 2 to 1 over the plane with these 4 branch points. So it's the genus 1 surface. This one here has 6 branch points. It's a genus 2 surface. It's a little bit hard to imagine these, but in between, inside this, over this region is like a pillow, because you have 2 sheets crossing here. That's the top and the bottom of the pillow. And then these are the seams of the pillow. Okay. And so in each region, you have a flag. And in this case, because it's just 2 sheets, that flag is a 2-step flag, which is equivalent to just a point in P1. And this transversality crossing condition says that this flag is different from that flag. So up to P1, up to PGL2, I can fix 3 of the flags to be 0, 1, and infinity. The 4th flag is then not fixed and must not be 0, 1, or infinity, because it neighbors this one, it neighbors this one, and it neighbors that one. So we get a pair of pants as the moduli space of objects. This Lagrangian genus 1 surface is called the Clifford torus. It does not have an exact Lagrangian filling. Neither does this genus 2 surface, but it doesn't have a name. And I don't know if most of the Lagrangian surfaces that you construct this way will not have names. And we can study what the moduli space of object is, if we like. We have to choose a point in P1 for each region here, and the outside region, because this is happening in S2, so the outside region is compact. And this blue graph represents the dual graph, which is a triangulation. Yes, which is a triangulation. Dual to a cubic graph is a triangulation. And for each vertex of that triangulation, we need to choose a flag, and these flags must be different here. So if we take the points as flags over FQ, finite field, then there's Q plus 1 points, Q plus 1 possible flags, which I'm going to call that capital Q. And we can think of then choosing a flag as the same thing as coloring the points on this graph. And neighboring vertices must be given different colors. So we just have a coloring of the graph, and the counting of such things is well known. It's the chromatic polynomial of the graph, and that's the number of points in this moduli space. Modulo the number of points in PGL2, which is this Q, Q minus 1, Q minus 2. Okay, so that's good. Now, it's an important fact that as you do isotopies, these categories are unchanged. This is a theorem of Guillermo, Kashiwar, and Shapira. And so that means that the chromatic polynomial will distinguish Lagrangian surfaces. And so it's an invariant of these Lagrangian surfaces. So you get almost for free, but Guillermo, Kashiwar, and Shapira paid for it. Does that make sense? Gabe, let's see, you were giving me a thumbs up before. Are you still here? Uh-oh, he's not here. Oh, wait, thumb is I can't see where, yeah, thumbs up, thanks. Okay. Let's see what else. So yeah, that's how the modular space works. There's a flag for each region. There's this transversality condition across when the regions abut. And as I said before, you get this open Bott-Samuelson variety in one dimension. And you can sort of study this modular space locally because it's a modular space of sheaves, and you sort of provide the data here up top. You can provide data here on the bottom, and then glue in between. Take the fiber product. They have restrictions to the interface, and take the fiber product over the interface, and you can construct these modular spaces by such gluing methods as well. You could then try to analyze the whole problem as a planar algebra, gluing these objects this way. And that works for two graphs, for the case where you just have these cubic graphs. And there's a chromatic algebra that you can make from that, one that was studied by Fendley and Krushkal and Agel. But as far as I know, it doesn't really help in the study of higher sheeted covers. Okay. So in the interest of time, I'm going to sort of move away from that. What is the topology of the surfaces described by these decorated graphs? Well, because the vertices of the graphs are just branch points, when you have two vertices connected by an edge, you just think of that in the usual way as a branch cut. And around that edge, you have a one cycle, a loop. Here's two edges meeting. There's a loop around here and a loop around here. And if you just sort of see whether or not they actually intersect, they'll intersect at one of these two meetings, not both of them, because they'll be on the wrong sheets upstairs to intersect. Does that make sense? Francis, I see you partly with me. Yeah. And so the so then you can define the intersection pairing to be +1 if they intersect like this way, and -1 for the edges going the other way. There's two cyclic orderings of edges, three edges meeting at a point. There's other one cycles, which are a little less obvious. Here's one where there's one of these triple intersections, one of these hexagonal vertices. And there's a little Y-shaped pattern here. And there's a one cycle that goes around. If you sort of follow that Y, take the neighborhood of that Y, that will define a one cycle. Likewise, you can go sort of right through. Your branch line can go through one of these triple intersections. The sort of offending third plane really has no effect on you, and you get another one cycle that way. So basically, whenever you have a tree inside your graph, a tree formed by either going right through or branching at one of these hexagonal vertices, you get a one cycle. Okay, so that's the topology of these surfaces. And then you can ask, well, how do surfaces relate as you make changes in these patterns? For example, if you take these two trivalent vertices and you make them kiss, that's taking a connect sum of the two things. That's not too hard to see. This is sort of a neighborhood of the vertex. Here's another neighborhood, and you sort of glue them together. There's mutation is affected by taking this edge and replacing it by that edge. So that's a mutation process. You can do a connect sum with a torus by taking an edge and taking its blow up in this way. So the topology of mutations, connect sums can be studied through this diagrammatic technique. now I want to make some contact with cluster theory. So from 30,000 feet, what do Lagrangian curves have to do with clusters? So here I've drawn in red a Lagrangian curve. In L, in blue, this L is an exact Lagrangian filling of that curve. And the way we want to think about that is this exact Lagrangian, think of it as an object in some Fukaya category, specified by its boundary conditions at infinity, which is this Lagrangian surface. And if you had such an object, then you could put different local systems on that object and get a whole chart of objects, a torus chart. And there'll be a chart of objects in this category defined by this Lagrangian surface. And what we did in earlier work with David Truman and Harold Williams and Vivek Shenda is analyze, well, what happens if you then do one of these mutations on this Lagrangian surface? And then look at a filling of the mutated Lagrangian, then you would get another chart. And if those, sorry, not that mutation, but let's see, let me collect my thoughts. What I'm talking about is the square move. So it's I don't know if I can draw the two Lagrangian curves. But yeah, unfortunately, if I can't draw on this page, it's a little bit hard for me to draw which Lagrangian curves I'm talking about. But there's these are Lagrangian curves associated to the square move on bipartite graphs, which is like the basic mutation in cluster theory. And those Lagrangian curves are related by isotopy. So what we found was that if you take a filling of one curve, then isotope the curve, and take a filling of that, those two fillings define different torus charts. And those charts are related by cluster mutation. Okay, and so how does this surface story help inform that? So imagine that you have one of these diagrams. In black, I have a cubic planar graph, but drawn not on the two-sphere, but on the disk. So it's literally just this. It's not more than this. It doesn't extend further. So over that graph, I would imagine a two-sheeted cover over that disk. And the boundary of that disk, I have a two-sheeted cover over the circle. So now I'm actually talking about Lagrangian link or graph. And that's what I've drawn in red. Now in black, what I have is a Lagrangian surface, and the boundary of that surface is this red Lagrangian link. Now here's the key point, is that because there are no closed regions in this black graph, there's going to be no Reib chords of that Lagrangian surface. Which means that when you take the Lagrangian projection, if you go way back and where I define the Lagrangian projection, you actually get an exact Lagrangian. So if you take the Lagrangian projection of the Lagrangian surface described by this black graph, you get an exact Lagrangian manifold, and it's embedded because there are no Reib chords. Reib chords are self-intersections of these exact Lagrangian. Great. So what is that? That's an exact Lagrangian filling of this Lagrangian knot, this red Lagrangian knot. And so in this case, if I have a 2n knot, what have I drawn? I've drawn the case n equals 1, 2, 3, 4, 5, right? You can ask, well, how many ways are there to draw a cubic graph that has no regions, no closed regions in it? And that's a dual to a triangulation of a 5-gon, right? Or, you know, more generally, a triangulation of a, I guess it'll be whatever n is. And there's a Catalan number of ways of doing that. And so you find a Catalan number of fillings of these knots in that way.
Sorry for one question. So you're talking about a Lagrangian surface with boundary.
Yes.
And you're saying the boundary also forms a Lagrangian?
Legendrian knot boundary. This is a exact Lagrangian. Because I'm taking the Lagrangian projection, I get an exact Lagrangian
I see.
surface. And as long as I make this radial, so that surface will be sort of conical at its boundary, then it defines a Legendrian knot at its boundary.
Okay, okay. Okay, sure. Yeah.
Right. Great. So if I may go for a few more minutes, because I have all my problems starting, but I understand if people have to leave. So I have sort of a punchline here. And Jan, I'm going to have to skip this, that part. So if now I have a more complicated knot on the boundary, maybe a 3-sheeted cover, how many can I construct fillings by taking diagrams in some clever way? So one application that we have of these methods is to construct infinitely many non-isotopic fillings. So one thing to say is that sorry, I should have said this earlier, that these two cluster charts must be non-isotopic Lagrangians. If they were isotopic Legendrians by the Guillermo-Kashiwara-Shapira theorem, they would have defined the same chart. It wouldn't have been different. So when you take a filling and then you move it with a cluster mutation, you get a different filling. Okay, so that's the idea, is to realize mutations on Lagrangian fillings that you can construct using these diagrammatic techniques. All right, so this is my last slide that I'll discuss, and it'll be how to do that for an example. So talking to Dylan Thurston, you know, he pointed us to this diagram. So this is a quiver with 1, 2, 3, 4, 5, 6 nodes and some arrows. And 1, 2, 3, 4, 5, 6 are just the label of the nodes. These are not multiplicity on these arrows. And you can mutate and go to different charts of a cluster variety described by this quiver. So let me put delta to be the sequence of mutations, mu1, mu2, mu3, mu4, mu5, right? Namely, mutating at 1, mutating at 2, mutating at 3, mutating at 4, mutating at 5. I'm never going to mutate at 6, so it's essentially frozen. If you do delta n times, you get a new quiver, and it looks like this. Slightly different from the old quiver. This 6 has spawned an n, an arrow to each of the other ones with multiplicity n. The arrow from 1 to 6 has gained a multiplicity 2n plus 1. And if n equals 0, it's just the original diagram. Because these n's are different, these represent distinct cluster charts on an infinite number of distinct cluster charts on the cluster variety defined by this seed. Okay, and so great. So now that's our challenge, is as long as we can realize these mutations diagrammatically, we get an infinite number of fillings. And we will be able to do that. So here is a realization of this cluster variety. So in the dictionary to cluster theory from these Lagrangians surfaces, the intersection pattern is encoded by the arrows. So let me show you how this quiver is described by this surface. These branch lines, these branch cuts in purple, 2, 3, 4, 5, represent the nodes of the original quiver. 6 is going to be this one, another branch line. And 1 is going to be this interesting one. It's this tree here that goes like that. As I said earlier, to each tree, there's a 1 cycle. And so this large tree, 1, is this cycle 1. And you can see that it intersects 2, it intersects 3, it intersects 4, it intersects 5, it intersects 6 in a different way. So the arrow with 6 goes in the opposite direction as the arrows with the other. And then we were able to figure out how does mutation affect these curves. What does mutation look like diagrammatically? It's not as simple as it was in the two-sheeted cover where you just had this, what is this, HI move, where, you know, this, to do that. It's a little bit more complicated. Sometimes it's simple, but to write down local rules for what it does, it's a little bit more complicated. So you spawn a whole bunch of different vertices. But we're able to write it down. And if you look, the boundary of this figure is the same as the boundary of this figure. Okay? So we have the same Legendrian knot at the boundary, namely, what is this? 2, 2, 2, 1, 2, 2, 2, 1, 1, 2, 2, and here it is here. That knot. And further, although it's complicated, there's no Reib chords in this diagram either. So you get an exact Lagrangian filling. And you can continue this and look at what the filling looks like. It gets quite messy, but so that's a result. Right, so when you look at these diagrams in a disk, you can construct these Lagrangian fillings. You can affect cluster mutations. And if you look at them in annuli, you can study concordances, and there's infinite sequence of concordances in the concordance monoid of some of these links as well. So that's some application of these new techniques for studying Legendrian surfaces, and that's what I wanted to discuss. So thanks for your attention.
Yeah, thank you very much. Are there any questions?
I have one question. So you mentioned there's no Reib chord. So what is the criteria to tell whether?
That's a great question. Unfortunately, we tried for quite some time to develop a general criterion for the non-existence of a Reib chord, and we couldn't do it generally, but we could do it specifically for this sequence of maneuvers. So actually, we could prove that upon mutation, if you didn't have a Reib chord, you can continue to not have a Reib chord. And the question is, can you construct these fronts for these Legendrian surfaces in such a way that their slopes remain distinct, so that you don't have the same slope. And the non-compactness allows you that. But you can see there are sort of closed regions, but there's not really entirely closed regions by a single color. And even when there are, you can further argue. So yeah, it's a bit ad hoc here, and I'd love a general criterion, but I don't know one, not yet. That's a great question.
Okay, more questions? Yeah, actually, I have kind of a question. So you have these n-graphs and the corresponding Legendrians. Sometimes they admit Lagrangian filling something. Don't, and there is this Fock and Goncharov formalism. They also have graphs and surfaces of different type, and they construct some cluster varieties out of this their graphs, which are different from yours, but the supply of cluster varieties in their case, is it, I mean, it should be different.
Which graphs are we talking about? Are we talking about bipartite graphs?
No, this zigzag graphs, I mean, this a little bit later.
Yeah, so given a bipartite graph, you can construct these zigzag curves. That's right. So that's sort of a one dimension down story.
No, not about, I mean, you wrote some picture with really Legendrian curve,
yeah,
which is a boundary of the Lagrangian filling. It's, again, it's a curve. It's not in 5-dimensional contact thing. It's, yeah, something like this, yeah.
Right. So let me just say something true and see if it's a partial answer to your question. If you take a triangulation of a surface, an n triangulation of a surface, you can construct from it a sort of a large bipartite graph, right? And then make the zigzag curves from that bipartite graph. And what you'll get is, so then if you have a exact Lagrangian surface bound in that curve, as you would if you take, let me answer it correctly. So what we showed with Truman and Williams and Schenda is that if you take a bipartite graph on a surface, you can construct a exact Lagrangian filling of that. And it'll be a filling of the zigzag curves. So if you take an n triangulation of Fock and Goncharov and the associated bipartite graph and construct a filling, you'll get an exact Lagrangian filling of these zigzag curves. These zigzag curves can be isotoped to be around the vertices of the triangulation. Sort of n concentric circles around the vertices of the triangulation. What we're doing here is kind of a subspace of the set of sheaves that you would get associated to those exact Lagrangian fillings. Namely the ones that have no monodromies at all around those vertices. I should explain that better. Let me try again. So let's just take the case of a 2 graph, like this one here or this one here. The Reid chords lie in the middle here, which are the vertices of the triangulation. Those are the self-intersections of these Lagrangians. If instead you puncture those, instead of have them be a self-intersection, then you get a possibility of a lot more objects. Ones that have non-trivial monodromy around that chord. So among the space of, or so this is you have some cluster variety of decorated local systems with monodromies around these punctures. But what we're describing through these surfaces, if you take the associated sheaves from them, you get decorated local systems, but with no monodromy around the puncture, just the information of the flag itself. Does that help?
Yeah, it helps a little bit.
So I only have the flag data here. I don't have any monodromy data.
Mm-hmm.
So it's weird. It's a decorated local system that's constant. Yeah.
Yeah, a bit strange. Yeah. Okay. All right. More questions?
Yes, I do have a question.
Yes.
So in your diagram here, sorry for the sound. So in your diagram here, you talk about the var groups. So mostly you are considering for the symmetrical groups here.
Yes. Yeah.
And other parts I'm not very clear, but Jody Williams and Ben Elias, they also describe some diagrammatic description of this kind of category with the more cluster grid groups acting on those
Right.
tensor categories, also producing, and some of the axioms looks, some of the properties looks very, very familiar, very close to theirs.
It is very close. So, that's right. But we can't, I know of no, because there's this natural ordering among, for Legendrian surfaces, I don't know any interpretation outside of, you know, the SN for the other groups. I don't know because any Legendrian surface interpretation.
I see.
Yeah. But yeah, their diagrams are pretty much the same as ours, and they have these Bott-Samuelson varieties, but they're not open, and so there's a little bit of a difference, and we're trying to figure out how to relate.
But Samuelson, and there is also analog of in terms of a so-called bimodule. That's probably where they got their motivation to do for more general cluster pictures.
That's right.
And you also look at the quiver, the example with the 6 vertices. That one you're doing the mutation, and you somehow the delta looks like a cluster elements for the the cluster group corresponding to that quiver without the 6. And the number 6 is frozen. So I see.
Okay, more questions?
Maybe I'll ask one more.
Sure.
So you mentioned, since you mentioned Dimer and that story, so Dimer was like in a 2-dimensional surface, you have some black and white dots and the trivalent graph, you put some zigzag, use zigzag as a Lagrangian. But so is there an analog story in the 3 dimension where you replace the trivalent graph by the analog of this trivalent graph and put some Lagrangian wrapping around that? So my question is like, what's the analog of a zigzag strand in 3 dimensions?
Oh yeah, these zigzag surfaces. Yeah, I spent a long time trying to imagine what that would be, and I don't have a good answer.
So because I read this paper by Ben Gamage and Nadler, and they have this honeycomb picture, and there they seems to be able to produce a some microlocal stock sheath, which is supposed to be related to this. I mean, at least in 2 dimensions, those are zigzag.
Yeah. How to answer that question? I mean, a cubic graph. Let's see. How do I want to answer your question? No, I don't have a good
That's okay.
analog. There's a lot of things that you can do. I mean, there's if you have a cubic graph, on the surface that's dual to a triangulation. And so we know sort of the three-dimensional analog of that in terms of a foam and a tetrahedronization. But I don't know how to construct all the gymnastics of surfaces, of zigzag surfaces. Yeah.
Okay, sure.
All right.
Eric, may I ask you another question?
Sorry.
So your 3D, kind of a basic 3D manifold with which you work is a product of a surface with a line. Can you replace it by, say, I don't know, like compact 3D manifold? I understand that kind of words cannot be simply
I
said.
imagine that you could possibly replace the line by a circle. I think you also have a contact form, contact one form in that case. So possibly you can get something there, but then it feels like there's going to be something infinite dimensional, because if you have this sort of rank one condition that it increases, and then comes back, you're not going to be able to realize that in finite dimensions. But that doesn't mean it's not an interesting thing to do. Sorry, I'm panicking a little bit because I'm at 3%. Either I have to run and get a battery, or
all right. So the very last question for 3% battery, if someone have one.
Could I ask about there's some connection to the spectral networks of Gayotomor-Knightsky. Could you say any words about that?
Yeah, let me maybe go back here and give me 10 seconds. I'll get the chart. Then I won't be panicked. In fact, I might have been able to give Pong a better answer if I wasn't so distracted by the need for electricity. Okay, unplugged it. Right, okay, so here is an n triangulation, or where n equals 3, and here's a single triangle.
Right.
And here's the associated, we just sort of wrote down the pattern that you can draw for an n triangulation. Here's the pattern it is, ignore the green, for a 3 triangulation in a single triangle. So this blue is one type of crossing. I have 3 sheets, and the blue is the crossing of 2 of the sheets, and red is the crossing of the other sheets. So now an object in the category defined by this this crossing is going to be, there'll be a flag here and a flag here and a flag here, and flags in between. But actually, because these are all the longest words, these flags are completely transverse flags. So the moduli space is some space of, configuration space of flags at vertices that are completely transverse to one another. And then, so what we might want to make contact with cluster theory is then to identify what are the cluster coordinates for the chart defined by this triangulation, right? And then as you go to a new triangulation, maybe you flop. There's another triangle, and then you do a flop here. You would then have relation among the cluster variables. So that's sort of the idea. So in thinking of these as spectral surfaces, the cluster variables are the monodromies around the curves of the surface. So each loop on the surface gives you some cluster variable. So as I was describing, in each triangle here, you would have a 1 cycle, which I've drawn in green. And it's up to you now to compute the monodromy of the 1 cycle defined by the flag data. And that should be the cluster coordinate. So let's do that. You can see that if you take that one cycle in green and just sort of isotope it, push it out to the boundary, it's actually this boundary triangle. And how do you compute the monodrome? So I'll just show you how to do that. The end result is that you're going to compute the monodrome to be this, what do they call it? Triple ratio of these flags, which is the cluster coordinate of Fock and Gontrop.
Right.
And so either I can walk you through that, I'm happy to do it, or just tell you that when you compute that microlocal monodrome, and what that means is that, so for these constructible sheaves, there's a map which maps to local system, to a local system on the Legendrian singular support, which means that there is some local system canonically defined along this green line, which is just part of the Legendrian surface. And the monodrome of that local system can be computed, and there's some linear algebra here, and it gives the same answer. So that's the upshot. And then depending on people's attention, I'm happy to walk through that calculation.
Well, so that gives you the same coordinate as GMN, right?
Yes. Yes.
So I guess I'm wondering, okay, so that's like some special case of their spectral network construction. So are the combinatorics, like, is there a more general matchup between them or anything?
Right. No, I don't think that we could do the general spectral network, but these special ones that are defined in this way, we can. Also, like, maybe it's worth saying that, like, so this, if you do like a flop of a triangulation, you can affect that. But there's sort of, you can also do all sorts of mutations in between, and you have geometric interpretations of these sort of partial mutations. So an actual flop would be like, I don't know if you can imagine like another triangle here. This half edge would close up, and there'd be a closed blue edge there. There'd be a long edge here. There'd be another one there. And the flop is really a sequence of smaller mutations that you can do. And you can do each of these. So I don't know.
Okay. Okay, thank you.
All right, more questions? Well, there are no more questions, so thank you, Eric, very much for the wonderful talk.
And thank you for putting up with all my technical difficulties.
Yeah,
sorry, I totally
no, that was fine, perfect. And well, have a good time in New Zealand.
Okay. Thanks, everyone.